So I'm Seth Chiasson. I'm acting as the group reporter for the jet engine experiment that we did last week. So I'm going to start off with giving a little recap as to what's involved with the experiment and a little bit of background as to how these are used and why it's important to understand it. And so the main purpose of this particular jet engine is that it's used as a peaker. This is only used during peak times during the day where, let's say, middle of June, everybody has their AC running and it's too much load on the grid. So to quickly generate more power, they'll start using these at the peak times of the day. And so this is a little recap as to how it works. Similar to any other engine, you're going to have an intake, some kind of compression, fuel addition, and you're going to combust it and then extract work from it. So two main components that are going to be referred to a lot is the power turbine right here, as well as the free turbine. So the power turbine is actually only used to generate enough work to turn the compressor, so that way we can suck in more air. And something that's interesting to note about that is that because you only need to generate enough work to run that compressor, the efficiency only looking at that compressor is actually really small. Reason why that's important is because if you over-design that turbine, you'll actually be taking out an unnecessary amount of energy from the system, and that'll reduce in the end how much power you're actually generating, how much power you're getting out of the alternator. So, as mentioned earlier, you have a compressor, you have a combustion area, the first turbine which returns work to the compressor, and the rest of it will go to the free turbine where it turns a rotor that generates an alternating current, and therefore you get power. And so, using some air tables at different stages, for example, the compressor inlet, I used atmospheric pressure, but after it's compressed, it goes up to about 1 atmosphere, so that's where I use the tables to get these enthalpy values. And so, as shown, the compressor, the first turbine is only about 19% efficient, but as far as the amount of work that you get out from the entire system, it's about 42%, which makes sense for standard engines. And so this is a description as to how the power is actually generated in the system. So the main concept that this uses is Faraday's law, where if you have an alternating or some kind of electro or magnetic force passing through a set of coils, it'll actually generate a current. And so this rotor is being turned by that last free turbine in order to generate our power. And so it's the rotor only acts as an electromagnet. It's not a permanent magnet. So this is going to be the data that we collected. Main things that we're going to be looking at is the voltage and the current, and therefore the power that it was able to output, as well as the engine and generator RPMs to see the trends of how those are related, and most importantly the fuel flow, which has a very interesting trend to it. And so something to note with most of these plots, you're going to notice that there's a peak and then a dip and then back to steady state. That peak is whenever we had the engine essentially run away from us and ended up shutting off. And so we had a small little reset stage, and then eventually we got back to steady state. So here you can see the power, the voltage and the current, which are directly correlated with each other, and therefore as well as the power. We ended up getting about 1,200 watts out of the system once we reached a steady state condition. And at that power generation, our generator was spinning at roughly about 8,000 RPM, and the engine was spinning at about 45,000 RPM. So we made sure before we, at the beginning of this experiment, we reached a steady state condition of about 55,000, just to make sure that everything was running smoothly. So, what's most interesting about this fuel flow chart is that once we reached a steady state condition, the amount of fuel that we were actually consuming went down, which almost seems counterintuitive because that's the area where we were generating the most power. And so I'll try to explain that a little bit. And so one of the things to calculate for this was the fuel to watt efficiency in terms of how much you're consuming per minute and the amount of energy that you get out of it. I was really surprised by this because as calculated, at the peak efficiency, we were only consuming about 3.2 times 10 to the negative fifth liters per minute for every watt that we were generating. And so for the amount of energy that we were creating, 1,200 watts, we were actually consuming very little fuel, close to about 2.3 liters per hour to generate 1,200 watts. And so in conclusion, the jet engine power generators, they create a very large amount of power for how much fuel that they consume. And something that was noted was that the power turbine is designed to only produce enough power to run the compressor, so that way you're not pulling out too much energy from the system. And something that was interesting to note was that there's definitely a benefit to using high flash point fuels such as kerosene or diesel, if that is possible, as you can pressurize these fuels and add heat to them before they ignite, and so therefore you're able to put more energy into the system. And so just for reference, the fuel content of kerosene is about 132 megajoules per every gallon. And so that's pretty much everything. So if you guys have any questions.